Contrary to what most people learned about it, scientists now understand that our moon has an extremely thin atmosphere. It is probably the most common type of atmosphere in our solar system, but very little is known about it. During several of the Apollo missions, astronauts saw a glow above the lunar horizon. These rays and streamers reached quite high, possibly suggesting that dust is being lofted to great altitudes. These astronaut and earlier robotic observations prompted several theories about why this happens. Are meteoroid impacts or electrostatic forces lofting dust above the surface? Is there dust in the moon's atmosphere? Even the nature of the moon's atmosphere is still a mystery. NASA will attempt to answer these enduring questions with the Lunar Atmosphere and Dust Environment Explorer, or LADEE, mission. Designed and built at NASA Ames Research Center in collaboration with NASA Goddard Space Flight Center, the LADEE spacecraft will use multiple instruments to measure the density and composition of the lunar atmosphere as well as the dust in it.
Other spacecraft and instruments have been launched to the moon before, but nothing like this robotic mission, with its purpose and ability to precisely measure the environment above the lunar surface. What we hope to learn from LADEE is a means to gain a better understanding of the structure and composition of the very thin atmosphere of the moon, known as a surface boundary exosphere, and also how much dust may be in the lunar atmosphere. We're looking at environmental properties on the moon, such as electrostatic charges that possibly levitate dust off the surface into the sky.
The LADEE spacecraft is 6.5 feet tall and weighs 844 pounds. LADEE will be the first payload ever launched on the new Minotaur 5 rocket from the NASA Wallops Flight Facility in Virginia in September of 2013. It will also be the first deep space mission to launch from Wallops Island. 1 month later, the spacecraft will go into lunar orbit after a thruster burn slows the spacecraft so that it can be caught by the gravity of the moon. LADEE will enter into a retrograde orbit 156 miles above the moon's equator, circling in the opposite direction from the rotation of the moon. After 30 days of system checks, the spacecraft will descend to about 31 miles above the surface and begin science operations for the next 100 days. Due to variations in its orbit, the spacecraft will fly at times as low as 12.4 miles above the surface of the moon. This low orbit will enable LADEE to gather extremely precise data using 3 instruments.
One of the instruments, called the neutral mass spectrometer, will take what are called in situ or in-place measurements of the atmosphere of the moon. The second instrument is the ultraviolet and visible light spectrometer, and it will take remote measurements of both the atmosphere and dust from a distance. The third instrument is the Lunar Dust Experiment, and it will directly measure dust particles and analyze their masses. The fourth instrument, the Lunar Laser Communications Demonstration, will test the effectiveness of high-bandwidth, high-speed laser communications from deep space.
LADEE is different from most other spacecraft built by NASA and will be a first in many ways. LADEE is the first spacecraft built using what is called the Modular Common Bus design.
Using the same basic architecture, any number of spacecraft can be developed using common bus components without having to design and build each from scratch. LADEE was designed and built at NASA Ames at a very low cost for a deep space mission. We took every opportunity to use components that were already flight tested. For example, we worked closely with our partner at Space Systems L'Oreal to build a variation of a commercially proven propulsion system that is in use on many of their satellite systems. LADEE was built to operate as efficiently as possible. We placed solar panels around its body so it could recharge while facing the sun from almost any angle. No extra components and very few redundant systems were installed. The overall system was developed to support the basic requirements of the instruments with no extra power to spare. We expect LADEE to successfully demonstrate the benefits of a multi-use design, which could enable more missions in the future by dramatically reducing the time and cost to build a spacecraft.
LADEE will be one of the first NASA missions to actively recruit the public to make observations in support of the science team.
During science operations, we want to collect information about any meteoroid impacts that occur on the surface of the moon. Telescopes of 8 to 14 inches in diameter are ideally suited to record the flashes of meteoroid impacts on the moon. Now, this is a size of telescope that many amateur astronomers and schools have. We want to assemble a network of observers around the world to capture these events during our mission. We can compare this information that we get from our Earth-based observers about meteoroid impacts on the moon, their location, the time that they happen, with any changes that LADEE's instruments see in the structure and composition of the lunar atmosphere, and even the possible amount of dust that may be lofted into that atmosphere. But even people who don't have telescopes can make valuable science observations for the LADEE mission by simply going outdoors and counting meteors in the nighttime sky. NASA's Meteoroid Environment Office has made this easier for them by coming out with a smartphone app called Meteor Counter that helps them count meteors and actually send that information to NASA.
LADEE will continue to gather data right up until the last moments of its mission. As LADEE descends to its final resting place on the moon, it will send data of the dust it encounters on the way down. Even the impact itself could be observed using the Lunar Reconnaissance Orbiter for any science that can be learned from the LADEE impact.
The moon still has secrets for us to uncover, and there's still much for us to learn about it. LADEE will help us better understand our moon, but also other similar bodies in our solar system, such as Mercury, some of the larger asteroids, and even some of the moons of the outer planets. This will benefit us in our future explorations throughout the solar system.